Hello everyone. So far we discussed about Nyquist sampling theorem and reconstruction of original signal from the knowledge of samples. We know that original signal can be reconstructed from the knowledge of samples by passing the samples through a low pass filter. So today we will do some numerical examples related to sampling theorem. Consider a signal xt equal to 10 cos 500 pi t is sampled at Nyquist rate. Find the sampling frequency. We know that the sampling frequency should be greater than or equal to twice the highest frequency present in the signal. Here fs is the sampling frequency and fm is the highest frequency present in the signal. We know that, so given signal is xt equal to 10 cos 500 pi t. So generally we know that cos 2 pi fc t, right? So comparing these two equations, we can see that, so this is equal to 10 cos 2 pi into 250 into t. So here we can see that fc, this is not fc, this is fm. Okay, fm equal to 250. Now fs should be greater than or equal to 2 into 250. So greater than or equal to 500 Hertz. So for this signal, the sampling frequency should be 500 Hertz. So we will do one more problem. Consider an analog signal represented by gt equal to 3 cos 200 pi t plus 10 sin 100 pi t minus cos 100 pi t. Find the Nyquist sampling frequency. So in gt we can see that it consists of three frequencies. F1 is, so cos 2 into 100 pi t, right? So F1 is 100 Hertz. So here F2 is, this is F2, this is F1 and this is F3. F2 is 50 Hertz and F3 is again 50 Hertz. Now the highest frequency present in the signal is F1, right? So now the sampling frequency should be, Fs should be greater than or equal to 2 into 100 Hertz. This is greater than or equal to 200 Hertz. So here the sampling frequency is 200 Hertz. So we will do one more problem. Determine the Nyquist rate and Nyquist interval for the analog signal represented by gt equal to 2 cos 400 pi t into cos 100 pi t. We know that 2 cos A cos B, it can be written as cos A plus B plus cos A minus B, right? So similarly gt can be written as cos 400 plus 100, that is 500 pi t plus cos 300 pi t. Now f1 is 2 pi f1t, right? So that is f1 is 250 Hertz and f2 is 150 Hertz. So the highest frequency present in the signal is f1 is 250 Hertz. Now sampling frequency should be greater than or equal to 2 into fm or greater than or equal to 2 into 250 Hertz. So that is fs greater than or equal to 500 Hertz. Now what is Nyquist interval? Nyquist interval Ts can be written as 1 by Fs, so which will be equal to 1 by 500 Hertz, which is equal to 2 milliseconds. So the Nyquist interval will be 2 milliseconds. Now we will do one more problem. Determine the Nyquist rate and Nyquist interval for the signal gt equal to sinc 100t. For doing this problem, we need to know the Fourier transform of a rectangular function. So consider a rectangular function in time domain. So if you take the Fourier transform of this rectangular function, you will get a sinc function. So how will you represent this rectangular function? This rectangular function is written as a rect t by t. See, a is the amplitude of the rectangular function, rect t by the denominator is the width of the rectangular function. Now if you take the Fourier transform, you will get it as a t sinc ft. That is the product of the width of the rectangular function into height, that is at, into sinc ft. So this will be the sinc ft, width of the rectangular function. So if you plot this sinc function, it will be 1 by t like that, because it is in frequency domain. So please remember this identity, that is the Fourier transform of a rectangular function is a sinc function, that is a rect t by t. If you take the Fourier transform, you will get as at sinc ft. Similarly, a sinc function in time domain, if you take the Fourier transform, you will get a rectangular function in frequency domain. So in the given problem, given that gt is sinc 100t, that is given that a sinc function in time domain. So we need to correspondingly we can convert this to a rectangular function in frequency domain. So in the given problem, we can write it as sinc 100t, that is a sinc function in time domain. If you take the Fourier transform, you will get it as, so since we are not interested in the amplitude, I'm not taking that amplitude. So rect f by, see here we can see that this thing will come under denominator, right? So similarly in frequency domain also it can be written as rect f by this thing, right? So if you plot this rect f by 100, we can see that, see, this t is the total width of the rectangular function. So total width is 100. So this is 50 and this is minus 50. Now what will be the maximum frequency present in the signal? The maximum frequency present in the signal is 50 Hz. So here fm equal to 50 Hz. Or now sampling frequency should be greater than or equal to 2 into 50 or greater than or equal to 100 Hz. So it will be very easier if you convert this type of problem in frequency domain. So now coming to the next problem. Determine the Nyquist sampling frequency for the signal gt equal to sinc square 100t. So for this type of problem also, if you convert it to the frequency domain, it will be very much easier. So we know that gt is sinc square t means sinc 100t into sinc 100t. So in time domain, sinc 100t into sinc 100t is equivalent to convolution in frequency domain. That is a convolution of two rect function, right? No. So we know that sinc 100t can be written as rect f by 100, right? Rect f by 100 convolution rect f by 100. So we can graphically represent this rect function. We know that the total width of the rect function is 100. So this will be 50 and this will be minus 50. So total width will be 100. So this is f convolution, again 50 minus 50, total width is 100. So if you convert to rectangular function, you will get it as a triangular function of double duration. So minus 100, 100. Now what will be the maximum frequency present in the signal? The maximum frequency present in the signal will be, say, fm equal to 100. So Nyquist sampling frequency should be fs greater than or equal to 2 into 100. So fs greater than or equal to 200 Hz. Now please do a homework problem. Determine the Nyquist sampling rate for the signal gt equal to sinc 100t plus sinc 50t. Now coming to the last problem. A signal gt equal to 2 cos 400 pi t plus 6 cos 640 pi t is ideally sampled at fs equal to 500 Hz. If the sampled signal is passed through an ideal low-pass filter with a cutoff frequency of 400 Hz, what frequency components will appear at the filter output? So in order to do this problem, first we will try to plot the frequency components present in this particular signal. So for that, we can take the Fourier transform of this particular signal. That is g of f equal to, we know that cos 2 pi f0t can be written as e raised to j 2 pi f0t plus e raised to minus j 2 pi f0t divided by 2, right? So for each this cosine components, you will get e raised to j 2 pi f0t plus e raised to minus j 2 pi f0t components like that. So if you take the Fourier transform, we know that Fourier transform of e raised to j 2 pi f0t will be Fourier transform of e raised to j 2 pi f0t will be delta f minus f0, right? So if you apply these two properties, you can get it as delta f minus 200. This is 2 pi f, that is f is 200, plus delta f plus 200 plus here it is 1 by 2, right? 1 by 2, this 2 cancel. So here it is 1 by 3 delta f minus 320 plus delta f plus 320. So this is the Fourier transform of the given signal. And if you, this is not 1 by 3, this is 3, because 6 by 2 is 3, right? So if you plot, now we can plot this signal. So at 200 we have this frequency to 200 at 320 with amplitude. This is the amplitude 1 and this will be at amplitude 3 at 320. Similarly, in negative frequency also we have minus 200, 3, 320. So this is the Fourier transform of the given signal. So given that the given signal is ideally sampled at sampling frequency of 500 Hz, right? So we need to use the Fourier transform of the sampled signal. So Fourier transform of the sampled signal is given by g delta of f is fs into sigma n equal to minus infinity to plus infinity g of f minus n fs, right? So this is equal to fs into sigma n equal to minus infinity plus infinity g of f minus n fs is 500, right? Okay, so this can be expanded as fs into, so we know that g of f is delta f minus 200 plus delta f plus 200 plus 3 times delta f minus 320 plus delta f plus 320. So this can be written as n equal to minus infinity plus infinity delta f minus 500 and minus 200 plus delta f minus 500 and plus 200 plus 3fs into sigma n equal to minus infinity plus infinity delta f minus 500 and minus 320 plus delta f minus 500 and plus 320. Now we need to apply, we need to give values for n. So if you look at the question, we can see that if the sample signal is passed through an ideal low pass filter with a cutoff frequency of 400 Hz. So that means if you draw the frequency response of a low pass filter, whatever frequencies are present inside this low pass filter, right? So that is by filtering this sample signal, whatever frequencies are present at the output of this low pass filter, that we will need to check. So for that, if you put n equal to 0. If you put n equal to 0, whatever frequencies are present, the frequencies present will be 200 plus 200 minus 200, then minus 320, plus 320 minus 320, right? Now if when n equal to 1, what are the frequencies coming at the output of the filter? Not filter, what are the output frequencies? Frequencies will be, when n equal to 1, it will be minus 700, now minus 500 plus 200, that is 300, plus 300, then, so this is plus 700, then plus 300, then when n equal to 1, this will be plus 820, then plus 180, right? So this much frequencies will be present. Similarly, its mirror image will also come at the negative side also. So if you plot, so we need, so if n equal to 2, this will be 1000 minus 1000 minus 200, that is 1200, then 1800. So anyway, it will be coming outside. So if you outside the passband of this filter, so given the passband of the filter as 400, right? So this is 400. So whatever frequencies are present inside this 400, that we will need to check. So anyway, we have 180 is there, then 200 is there, then 300 is there, then 320 is there, right? Similarly, it's mirror image coming at the negative side also. So minus 180, minus 200, minus 300, minus 320. This is minus 400 and this is 400 Hertz. So this much frequencies will appear at the output of the low pass filter.